Hello, I'm the programmer from Team 14712 Ruckus Robotics. Today I'm going to be going over some OpenCv basics, and the example I'm going to be using is detecting the team prop in CENTERSTAGE. As of 2023, or as of the 2023 to 2024 season rather, the OpenCv library is included in the standard SDK, so you no longer have to install it separately. While I will be using CENTERSTAGE as an example, I am going to try to explain what things do and very kind of generalize it so that these skills are, applicable in future years, and also to kind of demystify some of it. I know it can seem daunting to jump into computer vision, but hopefully this helps a little bit. So we're going to start with creating a file here, just a Java file, that I'm going to call team prop processor. All right, and here we're going to implement the vision processor interface. And all I did here is I clicked commit option enter on Android Studio, and it lets me implement methods. The reason we have to do this is that vision processor is what we call an interface. They've said somewhere that we're going to have this idea of something called a vision processor. All vision processors will have some init function, process frame, which will process the frames, and an on draw frame, which will draw on the frames. But we're not going to make any implementation of it. It's up to the user to make these functions do things. So I think, and it's pretty self-explanatory. It runs once on initialization. Process frame is what's running repeatedly while the camera stream is open, or while the camera is open rather. You never have to call it yourself though. So you should never be calling like prop processor.process frame. It just kind of happens, and they handle all the stuff behind the scenes, so like it's never doing two at the same time, or it's never using old data and whatnot. So you really don't have to worry about that. You just have to worry about what's in it. And on draw frame is important because the new vision processor system with vision portals. If I edit this input image here is input frame in process frame, and I have another processor running, it will pass in the edited version of the frame. However, it's not really a big deal. I have found it's not like I've never had a problem with it. I don't think people will either. And we're not really editing it except for the final step, which really just for visualization is not that important. It's very easy to not edit it either, if need be. For this example for team prop detection, we're going to assume the camera can see all three spike marks, and we're going to assume they each take up about a third of the camera view. I'll go through how we're going to do this, and then hopefully it's should be easy to understand and easy to change around as needed based on your own situation. So like we said, we're going to look at a specific area on the frame, and we're going to use rectangles. We're going to say, and so here we want to import, as I type rect, it's going to bring us with import options, and we want to make sure we're using the OpenCv one, not the Android graphics one. We have a rectangle, we'll call it left rectangle here, and we'll define this in a second. You're going to need a middle rectangle too, and a right rectangle. Cool. And so now, before we start deciding where these rectangles go, let's talk about the coordinate system. OpenCv uses the top left corner of the frame as 0, 0. And the bottom right corner will be the width of the frame, and the height of the frame. That will be the coordinate. So here, we're just going to declare the left rectangle is a new rectangle. We're making our object here. And one of the options as a constructor is to pass in 2 points, and that's what makes the most sense to me. It's a little more organized, I think, and a little easier to edit later on. So I'm going to do it this way. You can pick any 2 opposite corners, whether they're top left, bottom right, or top right, bottom left. Doesn't really matter. I think left to right personally, so I'm going to use top left and then bottom right. So we're going to say, the top left is 0, 0, and the bottom right is, maybe a third of the width and the full height. personally, for this year's competition at least, I'm not looking at the entire image. I don't need to see all the way to the bottom because that's like the ground pretty much. And I don't really see the very top because that's above my team prop. So we could do something like 0.25 times height for our top left. And that would cut out the entire top quarter of the image. We wouldn't be looking at it, or rather, we're not like cutting it out. And this can be important if maybe your opponent's robot is bright red or bright blue, so you don't accidentally try to detect their robot instead of your prop. But for the sake of this example, I'll be leaving at 0, 0. You'll also note that I use decimals here for the multiplication. You can use fractions. It's just, I think, a little easier to edit with decimals. If like, I need it to be a little wider. Okay, I can make this number like 0.4. Whereas if it was 1/3, I'd have to think about, oh, what's bigger than 1/3? But maybe that works for you. You do you. So I'm going to repeat this process with the middle rectangle here. Top left corner, we're going to say, 1/3 of the width, because that's where the left rectangle ends, right? And we're going to still be at the top of the frame. Bottom right corner, 2/3 of the width, typing outside the parentheses, 2/3 of the width and the full height. Right rectangle, I'm going to say this is, 2/3 of the width, because that's where the middle one ends. And I know this is getting a little repetitive, but I promise it's almost done. We're going to say it ends at the full width and the full height, so the bottom right corner of our frame. Great, so now we've defined these rectangles, but we're not really using them yet. And so I'll get that into a second. But this is more or less everything we're going to do in init. And you'll notice that, I didn't really talk about this, but we declare our variables up here by saying we have an object, a rectangle object. We're going to call it red rectangle, but we're not going to assign it any value until init is run where it's assigned a value. This is because we needed to know the width and the height. We needed the width and height of our input frame. And this is only accessible within the init function, so that's where we create these rectangles. So now we're going to look at process frame down here. The mat object frame that we call frame is going to be our input. It's going to be an RGB image. So at the pixel 0, 0, it's going to have some set of RGB values. And RGB is normally great because it's pretty common and we think about RGB a lot. However, in this use case, we don't really want to use RGB because it is additive. And here I'm just going to show an example. So here's a red. It's just RGB 200, 100, 100, picked pretty random numbers. And now we're going to see what happens if we multiply all of those values by the same amount, if we multiply them all by 1.25 here. And we're going to see what it means for it to be additive. We see that we do that, it's kind of the same color. It's a little brighter and a little more red, but it really is ultimately the same color. And that's going to make it very difficult for thresholding red or blue, because the brighter it is, or the more blue or more red the thing is, it'll naturally have a higher RGB value, and that's just how it works. So we're not really interested in using RGB. I'm going to talk about a little color space that works a little better for color detection and thresholding, and that's going to be HSV here. So just gotta drag this over, and as you can see, HSV we usually represent as a cylinder, where the color, the hue, is the angle of the cylinder, of the circle. The saturation is how far in it is, and so that's how blue something is or how red something is. And the value is how bright it is. You can see how these all vary. And so what this means is we're able to separate how blue and how bright something is, an object is, from what color it is, and that lets us do color thresholding very easily. So to implement this, we're going to go back to Android Studio here, and I'm going to create this new matrix. I'm going to call it, let's just call it HSV map. You'll notice that I'm using all caps for these things because they're constants. Really, this one should be HSV mount, so I'll do it like this because it's being assigned to new stuff. I'm gonna instantiate this just an empty one, and now we're gonna take this RGB image, right, frame, and turn it into HSV, and then assign that new output to HSV mount. Thankfully, it's built in for us. So we're going to use image processing, right? So there's really two main places that you find OpenCv functions. It's either a method, so like frame dot something, right? This is a matrix. Or you can do core, which is OpenCv core, and then there's a bunch of stuff here. Or improc, or image processing, and there's a ton of stuff here too. You might have seen it at the top there, but we're going to use image processing. That's what we're doing right now. Convert color. Great. So it takes three parameters. The first is our source. In this case, our source is frame. Our output, where we want to store the data, is HSV map. And then it asks for code. But what does the code mean? All it really is just telling it what we're converting to and what we're converting from. And it's technically an integer, but you should really do image processing dot color, right? So it's saying we're processing color. And in this case, great, it popped up right there, RGB to HSV. So while we technically could have put in 41, having this here instead of just number 41, it's a little more clear to readers and to yourself later on, like what that actually means, what it's doing. So I think it's best to leave it like this instead of using the number. Great, so now HSV mat has been converted to HSV. How can we use this to, detect our color? For the sake of this video, I'm going to be using red because I think that's a little more interesting here. And yeah, so you see here, I'll just move that for a bit. There's red here all the way on the left and red all the way on the right. And so let's take a look at the HSV values. You see, as I'm moving left, the H value in HSV, the hue, the color, the number's going down, right? So about 0, I'd say, is red. Maybe to like 15. It's getting orangish, but it's still pretty red. So 0 to 15 or so. Now let's go all the way to the right. Where does red start? It's pinkish. Maybe around here, 340 or so. We can see this value number down here is red. Seems like all the way to about 360 is still red. So, sorry. Remove this window. I hope you guys were able to see that, but yeah. So now that's our hue down. We're going to say 340 to 360 or 0 to 20. Let me just make a quick note of this in Android Studio. 0 to 20 or 340 to 360. Cool. Now let's take a look at the hue and we looked at the hue, the saturation, and the value. As once we've selected the hue, as we move left here, we can kind of see that the saturation is going down. It's less red. So I'm gonna say somewhere around here is where I'd maybe stop calling it red. Maybe like 50%, a little less than 50%. For the sake of easy math, I will be using 50% because mental math is not fun. And how about value? As we go down, it gets darker and darker, and up gets lighter and lighter. When do we stop considering it red? And I'd say also around 50%. I'd say this is still red enough for us to consider it red. So let me just also make a note of this in Android Studio. Like 50% and 50%. All right, cool. And I think we'd all agree that if we have some red hue and it's all the way saturated and all the way bright, that is very red. So it seems like anything in between in this little rectangle here, we would consider red. So let's go back to Android Studio, and how are we going to do this? So let's first look at this bottom 0 to 20 for hue. And I'm going to create this thing, scalar, just to represent what we consider red, right? So I'm going to call it, let's just say, lower red threshold, or yeah, lower red threshold low. I know the naming's a little weird, but so what's the lowest hue value we consider red? 0. What is the lowest saturation value we consider red? And we said about 50%. So this the 0 to 255. 50% is like 120 or so. I'm gonna call it 125. And we said 50% for value too, so 125. Scalar lower or lower red threshold up or high, right? The high, like what is the highest hue we consider red, and what is the highest saturation in value? Now, here we said 0 to 20. And this is a very common thing that happens. It's not really it's not super well documented. There's no like super bold notes about it. But OpenCv uses here the HSV values are the hue is 0 to 180 instead of 0 to 360, so it can store it in one less bit. The reasoning why it's not super important, if that didn't make sense, just know that when you color pick online, it'll be 0 to 360 most of the time, and when you do it in OpenCv, you'll have to just take half that value for it to work. So in this case, online we said 0 to 20. Here we're just going to use 10. And the hue values are 0 to 250. The saturation and value numbers are 0 to 255. Whereas Google, the one said, they use percentage, so 0 to 100%. Some use 0 to 1, some use 0 to 255, some use 0 to 360. You just kind of have to convert the proportions. It sucks, but it's not the end of the world. So here we're just going to do full saturation and value, because we said that's still pretty red. Great, so now we're able to detect anything in this lower, in this lower band of red over here. How about for the upper one? So we're going to repeat this process. I'm not really going to, I'm kind of just going to go through it. I'm not going to talk through it a ton because it's the exact same thing, just with different numbers. So we're going to make the low, this threshold. We set that on 340, so divide that by 2, so 170 or so. You can go a little lower, maybe like 165. And we said, half the saturation and value is fine. Then upper red threshold high. We said all the way to 360. That's pretty red. Right. So now these first two define all the red at the bottom of the band, at the bottom of the spectrum. And these second two sets of scalars define all the red at the top of the spectrum. So what can we actually do with that? So I'm going to make two more mats called low mat and high mat. And you'll see why in a second. Great. So we're going to say, hey, everything, core.in range, everything in this range of color, we're going to make it white, right? And everything not in this range, we're going to make it black. It takes 4 parameters. The first is the source. We want to use the HSV mat, right? Because that's what we're looking at. The lower bound. So let's say lower red low. And then the upper bound, right? So lower red high. And where do we want to store this? That's what low mat is for. We're storing that data in low mat. So now low mat represents all the frames that are within this threshold that we set are going to be white, or the pixels rather, are going to be white. And if they're not in that threshold, they're going to be black. And let's do this again, but with a higher range. So HSV mat, lower or upper red threshold rather. And we're going to store this in high mat. Great. So now we've done the two individually. and we kind of want to combine them. So let's just make a new one. Call it, I don't know, detected map, right? Because this will represent all the pixels that we detected that are within the range we want. And we're going to do something called a bitwise OR. All that really means, let me put in the sources first. The first source is low mat, then high mat, and our destination is going to be detected mat. So what is the bitwise OR? All it means is we have these two sources, in this case, low mat and high mat. And if, let's say the pixel at 0, 0, if either of them are white, the output in detected mat will be white. If they're both white, it's white. If only one of them is white, it's also white. But if both of them are black, right, so it's in neither threshold, it's going to be black. Great. So now we've kind of combined our results. But what can we actually do now that we have this mat that represents all the pixels that were within our threshold? And so we're going to use this to detect, the prop, and we want to look at specific areas of it, right? So we're going to use the thing called a submat here. Submat basically means we're going to look at a smaller piece of the entire image, and in this case, we've defined these three areas that we want to look at. Perfect. So first we're going to use the left rectangle area. We're going to look at that. And this is just returning that smaller piece, the part of detected mat that falls within that area. So what can we do with this? Well, we're going to use this nifty function called sumLms. It's part of the core part. It's part of core, so core dot sumLms, sum the elements, right? Of this frame, and what this does is literally takes all the values, all the pixel values, and just adds them all together. In this case, black returns 0 and white returns 255. So a higher number just means there's more white, and a lower number means there's more black, or less things detected within that area that are within the thresholds we have set. So we're going to say double. Let's just call it left percent, right? We'll work on this. So left percent is equal to the sum of the elements, right? So how much white there is. The dot val at 0 is just grabbing that number because of the way it's returned. If we divide by 255, this tells us how many pixels within this specified area were white. Okay, great. And we'll do the same for middle percent. And let's just copy this over, so I don't want to rewrite it. Now we want to look at the middle rectangle, right? So we can pass that into the submat instead. And now let's look at the right percent. Great. So in this case, we could compare these three directly because they all have the same area. They're all taking up a third of the screen. But as I mentioned earlier, sometimes you want to limit the height or limit the width so it's as small of a detection as possible. So how can we make a fair comparison between these three? Well, why don't we just add some parentheses here? And what if we said, well, this percentage should also be based on the size of the rectangle, right? A larger rectangle should, there will naturally be more white pixels that were detected. So we're going to divide this whole thing by the area of the rectangle, right? So left rectangle dot area, or middle rectangle dot area, so on and so forth. Right, and now this is like actually a percentage because how many pixels were white compared to how many pixels are in the area. Okay, so now what do we do with this? You could, let's make a comparison. If left has the most percentage, then we should say it's in the left, right? If left percentage is greater than middle percentage, and these two amperands just mean this first condition has to be true, and this next condition has to be true for this to happen. the highest percentage, so it has to be greater than middle and greater than right. Right, so this just means left is the highest percentage. And then what middle will be the highest if it was greater than left, and if it was greater than right. I'm going to skip the commentary here. It'll just take me a second to finish writing these out, but the logic is all the same. Cool. But what do we do if it's not detected, right, at all? What if there wasn't a prop? We don't really know how this would react. It depends on the background too much. So what we're going to introduce now is a threshold, right? Some minimum threshold. I'm just going to call it, I'm actually going to do 3, 1 for each one. So like left threshold, let's just say like 0.1. And these are values you can play with. Ooh, mistyping everything today. Great. Any of these could be different values based on the areas and whatnot, but for now I'm just going to leave them all at 1.1. So what we really want to say is left is the largest percentage, and we're going to add that left, the percentage is greater than this threshold we've set. And we're going to do the same with middle. Middle has to be greater than the threshold. And right has to be greater than the threshold, than the right threshold. And if none of these are true, and this means the object was not detected at all, right? Teeth prop, to be specific. Cool. So now we have our logic down, but what can we actually do with this? A really easy way would just be say int object position, right? We're just going to default it to 0, for example. And say it was not detected, object, but we're going to set it to 0. If it's detected on the left, we're going to set it to 1. And if it's detected in the middle, we're going to set it to 2. If it's detected on the right, we're going to set it to 3. And then we'd add this other method here, like public int get object position. This will just return the object position. So now, every time process frame is called, this variable is updated, and we can return it. We can get the value just from this and do whatever we need in our autonomous. And there's definitely nothing wrong with this, but it makes it a little bit hard to read. So what we're going to do, instead of using the integers here, is use this really handy thing called an enum. They're kind of like cheats to storing information. They're incredibly useful, so I'm just going to do public enum. Oop, can't spell public. Public enum. Let's call this prop. This is prop location. We're going to do it all in uppercase. Prop location. Okay, and so here we're going to type. This allows us to store names of things. So if we have data with names, in this case, left, middle, and right, and we can also store associated information. Let's do a final int position number, we'll call it, actually. Public prop location, int position number, and then just set that equal here. Now we can also pass in a number if we want, and let's just add a not found 1, just because. So now we still get that integer here, right, of 0, 1, 2, 3 to represent where it is, but now instead we can create an object of this class called prop location. I'm just gonna call it prop location, right? That makes the most sense. It's gonna default to not found. Great. So if it's detected on the left, it should equal left, and this just makes it really a lot more readable. If before, I forgot what 1 means, but now it's literally called left. that would typically indicate it was detected on the left. And this makes code a lot more readable and a lot less likely to have small bugs. And in general, I think it's a great way to store information. I use it everywhere. Anything that's named, probably, in my opinion, it's better to do this than using integers to represent it. And so now that we've done this, we can do the same return that we had public, but now it's not returning an integer, it's returning a prop location object. Get prop location, right? And we're going to return prop location. But let's say we did want the integer for some reason, the associated integer. It's fine. Here you can see that we can do proposition dot position number, and if it's left, this will return 1. If it's middle, it'll return 2. So we can do all the same stuff too. Great. So now we've set up our detection and figuring logic to figure out where it is and a way to get that information. We can do one last thing. It's a convenience thing more than anything else. This should not be public, my bad. And that's just going to be, we're going to draw rectangles around the left rectangle, the middle rectangle, the right rectangle, and that makes it a lot easier to see, what is the camera looking at when it's doing this stuff, and also, is it detected? And so what we're going to do here, and so earlier I mentioned, if you edit this frame, it'll get passed on to other processors edited. And so I'm going to break a little bit of convention. Not that you're not supposed to do it, but it may affect things. So take this, these next few steps, knowing that if you are running another processor, you probably do not want to do this. Okay, with that out of the way, let's do core.rectangle, I believe it's called, or maybe it's under image processing too. It's under image processing. Okay, great. And so this takes, I know it's a lot of options, but I'm just going to use the most basic one, 3 parameters. The first is the image we want to draw on, in this case frame. And then what we want to draw, the rectangle, right? So left rectangle, and what color we want to draw. Now keep in mind that frame is an RGB, so the color is going to be specified in RGB. So let's just do a red border variable. It's a new scalar. Red is 25500, and let's do a green border too. So we're going to draw a green border around the rectangle that's detected and a red border around where it's not detected. Our green is 0, like this. Great. So what color should the left rectangle be if it detects it left? It should be green. And if it detects it left, then it obviously did not detect it middle. So that should be red. And it's also not right if it was detected left. Great. So now we're going to copy and paste this over and edit these in a second. If it's detected middle, we want left to be red and middle to be green. And we're going to swap it for the right detection too. Great. And then if it's not found, they're all going to be red. Cool. This was a very simple pipeline. We did hue thresholding. There's a lot more to computer vision. I personally find it fascinating, and it's one of my favorite things as part of FTC. I hope this was helpful. If you have any questions, leave a comment, or our Instagram is in the YouTube description. And if you're not part of the FTC unofficial Discord, I highly recommend it. I'm on there a good bit, so you can always DM me if you guys are on that and have any questions. So thanks for watching, and hopefully this is helpful and you guys can use this.